Hi everyone, I'm Yelo from Argonne National Lab. Today I will talk about QMCPACK performance portability on NVIDIA and AMD GPUs. This work is supported by the Exascale Computing Project. I will walk you through about how we designed the performance portable QMCPACK and a bit about the GPU porting details. Then I will show you the performance of the code. Let's start with the QMCPACK design. QMCPACK is a modern high-performance quantum Monte Carlo simulation code. It is based on C++ and adopts MPI plus X programming model. It has two main levels of concurrency. The name Monte Carlo indicates there are massive Markov chains to work with. They are called walkers. It is the coarse level concurrency. The name quantum indicates we are solving a many-body electron system. That's the fine level of concurrency. The number of walkers and the number of electrons defines the computational problem space. It is restricted to the lower triangle by a given hardware. The brown area is the target we would QMCPACK to perform really well. However, once the hardware is chosen, QMCPACK class drivers restrict good performance in a small problem space. We will fix that by introducing a new set of QMC drivers. Let's first look at the issues of classic drivers. In the classic CPU implementation, it operates one step, one walker at a time. Walkers are fully asynchronous. It's good for CPU, but it's bad for GPU. And also, each compute kernel is light. It's bad for GPU as well. Classic CUDA implementation in QMCPACK operates all workers in lockstep. It is good for GPU because kernels are heavy. However, the pre-post kernel operations running on a single CPU thread. When GPU could not be saturated in small simulation problems, you need using multiple MPI process targeting a single GPU, which is complicated. We also notice poor performance when the walker count is restricted by GPU memory in challenging problem sizes. The last but actually very important point, the legacy CUDA implementation have restricted features. We would like to change that. We are introducing a new set of batch drivers to overcome all the limitations of the classic drivers. We need to introduce a new concept called crowd. So walkers are subdivided into crowds. Walkers within a crowd operate in lockstep. Crowds themselves operate asynchronously. You can imagine when crowd size equals 1, it decays to the classic GPU driver. When crowd size equals the population size, batch drivers decays to the classic CPU drivers. But we recommend you to avoid forcing both these limits. By default, we will set the number of crowds equal to the number of OpenMP threads, making sure all the CPU cores are being used. Combining MPI and OpenMP, it fully utilizes all the CPU cores and GPUs within a hybrid node. So these new batched drivers are fully CPU-GPU agnostic. There's no code divergence at the driver level. In addition, batched APIs may fall back to existing CPU implementations. By doing that, we allow you to mix and match CPU-GPU features and making sure all the QMCPACK features are available. A bit more about GPU porting. In the pre-Exascale and Exascale machines, GPUs are from different vendors. So we choose to use OpenMP target feature to make QMCPACK portable on those vendor GPUs. OpenMP target also has a feature that allows you to fall back on CPUs for debugging. That's a very nice feature. Right now, for each vendor GPU, there are multiple compilers available. As explained about batch drivers, we use multiple CPU threads to launch kernels to GPU. OpenMP also brings optimization by overlapping compute and data transfer for me. So in addition, we also use GPU accelerated linear algebra libraries. So we specialize our code path to the very low level into CUDA or HIP to call those libraries. Intel porting for MKL is work in progress. Another point I want to mention, we maximize use of C++ templates to cover code variants like real complex valued wave functions and also for mixed precision cases. So let's talk about the performance. In the following slides, performance are defined as the throughput per GPU. A basic equation is workload divided by time. In QMC calculation, for a given problem size is the total number of workers per GPU divided by the total time. The total time can be break up as the sum of kernel time and GPU runtime overhead. The overhead is kind of constant, but the kernel time is proportional, roughly proportional to the number of workers. That's why on the right side, you see the figure indicates as the worker count increases, the throughput saturates. That's why when you do a GPU performance study, it is always required to do a worker scan to max out performance. Another limiting fact, more workers need more memory, so you may get limited in large problem sizes. Let's look at the performance of QMCPACK on Summit. On the right side, the figure is the throughput relative to the legacy CUDA implementation. We plot a wide range of problem sizes. For the largest problem size, the new code already way exceeds the performance of the legacy CUDA implementation. QMCPACK users run on a very wide range of problem sizes. If you look at the smaller sizes right now, the new code, the batch driver plus OpenMP is getting closer to the legacy CUDA performance. And there are still room to improve the performance. We started the porting from 2019, and throughout the releases, you notice that the performance improves steadily. So the code pass or test is very usable in production. How about AMD? Actually, QMCPACK runs reasonably well on MI100 AMD GPU. It is not fully bug-free, but improves month by month. Let's look at the performance. We did the study on Summit and Spark machines from Oak Ridge. So Summit has V100 NVIDIA GPUs, while Spark has MI100 AMD GPUs. If you look at the hardware specs, MI100 has higher memory bandwidth. It has higher single and double precision flops as well. Actually, it also has a higher host-to-device data transfer rate. So we ran 4 cases, the legacy CUDA code and offload code running on NVIDIA GPU. So you see the green bars. And the legacy CUDA code base being hipified and offload code on AMD GPUs. You see the red bars. So in addition, the legacy CUDA code base, when being used, it's solid bars, while offload code is in meshed bars in the figure. So let's first focus on the legacy CUDA code base. You see here, the AMD GPU performance is slightly lower than the NVIDIA GPU across the board, regardless of its higher hardware specs. But the gap is quite small. If you look at the offload cases, in small problem sizes, AMD is lagging behind NVIDIA. Look at the 16, it's about 40% slower. But indeed, AMD is still working on optimizing the OpenMP runtime, so further performance can be gained. If you look at the large problem sizes, AMD already runs faster than the NVIDIA. So offload code is better, taking advantage of the hardware capabilities on AMD. So please expecting further software improvements. I think so the performance will improve. So stay tuned. Summary. So with years' effort, we add the performance portable implementation into QMCPACK. So we open a new chapter. So over the years, we did a lot of work. Even I'm just presenting you the final result. We actually did the software technology exploration. We did prototype design in mini QMC and finally implemented in the full QMCPACK. So for QMCPACK users, please start migrating to this new implementation. Give us feedbacks. We will improve based on your feedback. We promise to continue delivering a high-performance code to the community, and it is performance portable across CPUs and GPUs from all the major vendors. So we are working on Intel. Expect similar code to run well on Ponte Vecchio or Aurora. Final point, we are working on putting more features and continue to optimize the performance for all the QMCPACK users. So if you have questions, you can reach me via email. If you have issues, please visit our GitHub website. Thank you.